Hello, everyone. Hope you have a very good break last week because there's no teaching. Then thanks for coming back. And it seems like there are not too many attendance this week. Maybe you're still enjoying the break. So can anyone hear me? Is everything good? Can anyone hear me? Is everything good? Great, thanks a lot. Thank you. So thanks for coming to today's lecture. And in the last couple of lectures, we are mainly introducing sensors. We're mainly introducing sensors. We introduced the camera and stereo camera and also RGBD cameras. And then it's the time-of-flight sensors. And then we introduced the fundamentals and also the data, some kind of like data and processing. Then in this lecture, before we start doing the lectures about the control, then we introduced a lecture which is called feature extraction and checking. This is what we are going to talk about. And in this lecture, we are mainly introducing first what is feature extraction and checking and why we are doing that. Keep this in mind. We have sensors, we have control, but why we have the feature extraction and checking between them, right? And after that, we will introduce different feature extraction and checking method. And the very traditional one is the Harris corner detection. It's a very old but very traditional one. So when I did my PhD, I do remember the first subject in the first project in the subject I used the Harris corner detection when I did photogrammetry. And then after that, there are two more popular feature extraction and matching method. One is called Sift, the other is called Surf. They are not quite young, but I mean, they are young comparing to Harris corner detections, but they are not that kind of young, but they are quite traditional. And also it works super well. So that's why we want to introduce that. Then the very last part in this lecture is about the RANSAC outlier removal. So when you extract the features, and then when you have some way to match them together, then there must be some outliers, which means the wrong matches, right? So you have most of them, the right matches, but you will definitely have some wrong matches. And this is the thing, and that is why we have this kind of like outlier removal method. And RANSAC is a very, very classic and also works very well method for this kind of outlier removal. It can work not only for this outlier removal, it can remove all the other like outliers in different kind of applications or different methods. So the RANSAC is an idea to remove the outliers. And it's really, really commonly used in so many areas. So that's why we want to introduce the RANSAC to the outlier removal. And in the handout activities, I think most of you have done something with Marlene in the last tutorial, because our lecture is a little bit delayed. I mean, these activities are mainly about the feature extraction and checking, and it's mainly about what we introduced. It's Harris corner, Sift, Surf, and RANSAC. Then you will find nearly most of them are really useful in your project or in your future career if you're still doing this kind of things. So and it's lots of fun as well. All right, then let's start today's lecture. Still have some students coming. All right, so at the beginning, can anyone tell me what is a feature? What is a feature? Why we call it a feature, not only a pixel on the image? So a feature is a local, meaningful, detectable part of an image. So a feature is still a part of the image, right? But it is local and meaningful and detectable part of the image. For example, a corner. So if you remember when you use the checkboard to do the camera calibration, then you use a checkboard. That checkboard has a lot of corners, and you need to extract the corners from those from the images of the checkboard. Then use the location of the corners to calculate the intrinsic parameters. Then that is kind of features. So corner can be a kind of feature, right? And the lines can also be a kind of features as well, and also squares. So what I mean is it's local. It's locally. You can't say from one image I get one feature. I get one feature. And why we can't do that is we need multiple features. We need enough number of features. I will mention it a little bit. Sometimes you need enough numbers of features that you can apply it in your algorithms or control or something, right? So for example, if you remember, in the future you may have the visual serving lecture, and then in that we need a minimum required of numbers of features. Then we can calculate the control of the camera, which is linear and angular velocity. So that is local. So the feature is local. It's locally located in the image, and then it's meaningful. Meaningful means you can use some model to extract them, right? And use that model. You are all extracting that kind of feature with the same meaning, right? That's meaning. For example, you only extract corners, right? Or for lines, for lines, you only extracting lines. And then the features extracted are having the same meaning, right? And also it's detectable. If you define a feature which can't be detected, then you can't detect the feature. You can't use that feature. That's meaningless, right? So the feature must be detectable. Then you can detect them and use them in the future, right? So that is the definition of the feature. Then the question comes to why we are using features. Why we need to use feature? All right. So there are several reasons why we are using feature. The first reason is the information content in the feature is very high. For example, if you have an image, instead of using one image, you're just using like 20 or 30 of corners distributed in the image, then it normally contains most of the information from the image, right? So the first is the feature contains high information from the image. That's the first thing. And then the next thing is it's most of the features, they must be invariant to changes of viewing point and also the illuminations. For example, if you want to use an image, and if the image will change a lot if you change the viewpoint or if you change the illumination, then if you directly use the image, it will not. And then if you still use the original image, then when your camera moves, you may not get some relations between them. So that's the thing. For example, if you have a handheld camera, and the most effective thing for the handheld camera is if you move the camera quite fast. If you move the camera quite fast, then the issue is just motion blur. Just motion blur. I think I mentioned that before in the camera lecture. Then you move the camera quite fast, there will be motion blur. But in this case, the most of the features they are different at that time. But one feature may works quite well in that case. That is the line. So for most of the applications, if they have this kind of motion blur issues, a line feature is the proper one. Then you can use. That's just an example. So the features can most of the features they can be invariant of changing of the viewing point and also the illuminations. Then which means your camera moves and then you find the relations. You can still track the features in different images, right? That's another thing. And the last is, and which is also very important is reduce the computational cost. For example, if you are doing the camera calibration and imagine you are using every single pixel on the image, then how much computational cost it will related to calculate this kind of intrinsic parameters. And then if you just use checkboard and you use the corners as the features, and then there are two good things. One is it's easy to check, right? So you have your board in each of the image, and then the distribution of the corners, which means the relations of the corners, you know that already. Then between different images, you can easily get the checking of each of the feature. For example, for corner 1, on image 1, its location is U1, V1, and in image 2, the same feature, the projection is U2, V2. It's quite easy to get the matchings or get the checking of the features. And another thing is the computational cost, right? The computational cost, if you're using every single pixel, it will be a lot. But if you're only using the corners of the checkboard on each of the image, then which means for each of the image, you're only using 20, 30, or 40 2D points instead of using a 640 by 480 pixels. That means it reduces a lot of cost, a lot of computational cost. But the condition is your feature contain most of the information on the image, and that is the case for the calibration, and that is the case for most of the applications. All right, so that is why we are using features. Then, what is good feature? I think I mentioned a lot of things before when we're talking about the definition of the feature and also why we're using feature, right? So what is a good feature? The good feature must be invariant of a lot of things. For example, the viewpoint, the lighting, conditional illuminations, and object deformations or partial equation. So which means a good feature means it fits the reason why we are using it. Right? So we are using feature, then we need to extract them from the image. And we need the feature has the ability to extract the features from multiple images, from different images. And also we want that feature the property of the feature will not change if we change a lot of things. If we change the camera, and if we change the if we change the motion of camera as well, right? So that's a good feature. The good feature must be invariant of most of things. In most of the real cases, if the feature is and the feature will be invariant to those kind of changes. That's a very good feature. And the feature has some other characteristics. The first one is the feature is better to be unique. The corner is not that unique, but you use the checkboard because it has distances, it has the relationship between the features already. Then the corner is already. Then some kind of like it's unique. If you remember when you do the camera calibration, and you manually select 4 points on the checkboard, and that motion gives the information about the location and also the orientation, which means the frame of the checkboard in the image, right? And then you know the distance, roughly the distance between each of the corner, or you know it's the distribution of the corners. Then it's quite easy to find the initial location of each of the corner. Then you apply a local searching of the corner, then you find the right corner, right? So that is what they did in the MATLAB calibration toolbox, which means it somehow is unique, right? So you want the feature to be unique, which means you find the feature in one image, you can find the feature in another image, and then you can link them together to do the checking. And also the feature is better to be unique. And then you can, for each of the time when you apply this feature extraction, you're checking, you are getting the same feature or the features with the same meaning, right? And another point is it must be sufficiently many. And this is what I mentioned before. So if you want to, so some applications, for example, if you want to calculate the relative pose between 2 images. So suppose you have a camera, it moved from one position to another position. Then you want to calculate the relative pose between the 2 cameras, the camera motions. Then you need at least 5 feature matchings. We call it 5 correspondences between the 2 images, which means you need at least 5 features on image 1, and you have the corresponding features on image 2. Right, so every single application, they have the minimum requirement, and your feature must fit the minimum requirement, and also as more as possible, because more features will get more accurate results for the estimation or optimization problem, right? And also as example of the calibration, then it's not using only one single square. Right, it uses checkboard. There are a lot of squares in it, and it's quite easy to get corners. And the corners must be like many, right? And why we are having those many corners is there is a minimum requirement of the numbers of the features they use in the calibration, and also the more features you used, and the more accurate you can achieve for the intrinsic parameter. All right, and the third one is it must be useful for the specific task. Then we will introduce a bit later. But some tasks they use just point features to calculate something, and some of the applications they may use the line feature or the block or checking a object or something. But that is it must be used in different tasks. All right, so that's the general idea about features. Then let me introduce the line feature, or we call it the edge feature. So the 2 of the features are what we really commonly used in the real application. The first one is edge, and the other one is point. First, let me introduce the edge feature first. So the edge feature in the image can be due to many causes. For example, if you look at the figures on the right, so the edge can be caused by the surface normal discontinuity. So if the surface normal, if you have an object, and if the surface normal is not continuous, then there's an edge, all right? And then if in the image, the depth, so if in the image a depth is not continuous, then there will be a line feature as well. So this is really commonly used in the RGBD camera. So if you have an RGBD image, for example, if you have a depth image, then by finding out the depth discontinuity, then you may find the edge as well, right? And another one is caused by the color is not continuous. If the surface color is not continuous. For example, if you have an object, and maybe you will use this kind of thing in your group project. For example, if you want to easily check a feature, and then you may use another color from the background, and then it's easy to extract. And also from that color, the edge it can extract it as well. But you may not use the edge; you may just use the location. And the edge can also be caused by this continuous illumination. For example, if you have light, then you have a shadow as well. Then there will be some edge on that. There's some edges on that, right? So the edge can be caused by many cases, but so that's why the edges can be easily extracted and be used in the real case. Then, sorry, wait a minute. Then, how can we extract the edges? So as we know, the edges is caused by the discontinuity of something, right? But from the image, this discontinuity can be represented by the gradient of the image. For example, if you look at the figure on the left, then you can see the gradient on the x direction has a value, right? The gradient means the changes of the intensity of the image. Then wait a minute. Then if you look at this figure, you can see the gradient has changed on the x direction. Then which means when we calculate the gradient on the x direction, then there is a large value. But from the other direction, if we calculate the gradient on the y direction, you can see the intensity on this direction will not change. Then which means on this image, in this area, you have a very large gradient on the x direction, but you have zero gradient on the y direction. Then which means you have an vertical edge, right? You have a vertical line, right? Then if we look at this case, suppose we have a horizontal line. Then in this case, you have a very large gradient value on the y direction, but you don't have gradient on the x one. So that is a horizontal line. But for most of the cases, the lines may not be exactly vertical or horizontal. But in this case, you can calculate the gradient on both of the two directions. And then you can use the arctangent of those two gradients to calculate the line direction. And then you calculate the theta, which is the arctangent of the two gradients. And that will be the line direction, right? And then the gradient value can be calculated as the mean square root of the gradient on both two directions. right? Then you can calculate the edge from it. And then if you remember, we introduced the the edge detection kernel for the convolution, and that is another way when you can you can extract the edge. And then you can, if you want to extract the edge, you can use the convolution with the edge detection kernel to make the pre-processing on the image, and then based on that image, then you can do the edge detection. Right, then let's come to the corners, or I would also want to say it as a point features, because in Sift and Surf, they are not merely the corner anymore, but they are point features. There's some kind of like a calculation with a constant meaning of the point features. They are not corner anymore. So as we can say, the intensity gradient exactly at a corner is not, so is ambiguous. So different from the line. We have from a line point, you can find one gradient. The gradient on this direction will be large, and on the other direction will be small. But for a corner, it's a little bit different. On the corner point, you can't detect too much things on the gradient. But if you consider the surrounding area, you can find the gradient on different directions. There will be large value, has 2 or more than 2. If it only has a gradient from one direction, then which means it's a line. But if you have the gradient with multiple directions, with multiple values, more than 2, then they're pretty much as a corner. And why they're using corner? The first thing is the corner is much more easy to detect it. I will show you about it a bit later. And also it's quite easy to match because it's a one-to-one relationship. It's a one-to-one relationship. But for the line, you are most likely to observe the line as a line segment, which means although it's a quite long line, but in the image there is a line segment. And the more important thing is the corner feature will contain more spatial information than the line. The line has more structural information, but for the spatial information, totally spatial information, the point has more that information comparing to line. Why is that? Because if you have a corner, the corner must be a one-to-one relation. One-to-one relation. But if you suppose you have points on the line, you can't find the one-to-one relation, right? So the point on the line can be any point on the line, any point on the line on the other line, right? On the matching line. All right, then which means if you have a line, this line can be any part of the other line because you cannot assume that you can observe the complete line segment. All right, so suppose the line is quite long, you're only observing one part, but one image you observe the part on the top, but on the other image you observe a part of the line in the middle. Then which means the two lines are the same line, but they are not in the same location. Then which means the line on the left image can be any part of the line on the right image. Then which means it doesn't contain as much spatial information as the corners. As that is spatial information, but for line features, it has more information for the structure environment. For example, if you are in a room with purely white walls, then the line feature may be a good feature to use. Then it can recover the structure quite easily. right? But if you want to have spatial information and you have enough information about the points, enough information about points, for example, your environment fully of colors and colors, and then it's easy to extract the points, then it's better to use points because it has more spatial information. Then let me introduce a very traditional, very old, but very commonly used detector, which is called the Harris corner detector. So Harris corner detector is quite old. I think it developed in 1950s or 60s or something. It's quite old. It's super old. It is used when we just have the digital images. So my PhD major is in the photogrammetry and remote sensing. It's mainly about photogrammetry. And when they do the photogrammetry in the very old age, they put the camera on the plane and then get the images to the ground. And then they do the corner detection. They do the point feature extraction, and they use the Harris corner detection. And as I said, my first project in the subject and is about calculating the relative pose between the two aerophotogrammetric images. When I did my PhD, when I started doing my PhD in 2007, then we use Harris corner detection. We use Harris corner detection to detect the corners, and then we use the 2D relations to do the matching, and then we use that matches, or we call it correspondences, to calculate the relative pose between the two images. This is what I did in a very, very early time. Then the Harris corner detection is mainly about detecting corners. For example, why we are using Harris corner in that case is all the photogrammetric images are in the civil area, so which means there are a lot of buildings in it on the image. Then for the buildings and roads, it's quite easy to extract the corners. There are a lot of corners there. So Harris corner is mainly detecting corners. It used the second order moment matrix to detect corners. The matrix is on the top right. It's on the top right here. That's the second order moment matrix for Harris corner detection. So which means in the Harris corner detection, you get an area of the image and you calculate this second order moment matrix. And for each of the term on the moment matrix, is only about the gradient. So Ix is the gradient on the x direction, Iy is the gradient on the y direction, something like that, right? And then after you calculate this second order moment matrix, then we use that second order moment matrix to extract if there's a corner or not. For example, if you look at this second order moment matrix, if the second order moment matrix has lambda 1 and lambda 2 on the diagonal, has a large value, but on the off diagonal they are 0, then which means for that point, when you are calculating this moment matrix, there are gradients on two directions, right? On two directions. Then which means it's a corner. But if we suppose lambda 2 is equal to 0, or lambda 1 is equal to 0, then which means you only have the gradient on one direction. Then which means it's not a corner, it's a line, right? So this is the Harris corner detection, and we use the second order moment matrix to extract the corners. Then let's move to Sift Feature. So horizontal corner detection is not invariant to scale, and it's not invariant to rotation as well. So which means it's not a very good feature, right? So when we do horizontal corner detection, it's mainly about the milling. So because we are on the image, there are a lot of corners, then we want to extract the corner. Then for that purpose, we are doing the horizontal corner detection. But it has some disadvantages of horizontal corner detection. The first thing is it's not invariant to scale and rotation, and which means it's not a good feature, right? So we can't say it's good, but it's relatively not that good feature. And another thing, which is more important, why we are not using horizontal corner detection at the moment is it doesn't provide the matching. You are extracting the corners, and after you get the corner, you need to get the relation. You need to get the relation of that corner. Then you can compare. Then you can say this corner on image 1 is that corner on image 2. But for horizontal corner detection, it's only a corner detection. And we don't have this kind of relations to tell the matches, to do the checking. And this is another disadvantages of the horizontal corner detection. Then people are trying to propose a lot of feature extraction and checking method. And until we have Sift. The full name of the Sift is called the Scale Invariant Feature Transformation. So the Sift is to detect and describe the local features in the image. That's the purpose. And this work is proposed by Professor David Lowe in UBC, University of British Columbia in Canada. And the first paper about this is published in ICCV 1999. So the ICCV is one of the best conference in computer vision. There are 3 best computer vision conferences. One is ICCV, it's called International Conference on Computer Vision, and the other is called European Conference on Computer Vision, which is ECCV. So it's the conferences will hold every 2 years. For example, this year if it's ICCV, and next year will be ECCV, something like that. And then the third one of the best at the top computer vision conferences is CVPR. It's called Computer Vision and Pattern Recognition. So those 3 conferences are the top conferences in computer vision. And it's really, really hard to get in. It's really, really hard to get in. And that paper was first published in ICCV 1999. And then the refined version is published in IJCV, International Journal of Computer Vision, in 2004. So the IJCV is one of the best journal in computer vision, and is also one of the best journal in engineering as well. So if you remember, I mentioned the paper for the camera calibration, right? So that paper is published in PAMI, so i.e. transactions on pattern recognition and on pattern recognition. So that is PAMI and machine intelligence. So the PAMI and also IJCV are the 2 top journals. In computer vision and in engineering as well. It's really hard to get in. And the refined paper is published in IJCV. Then this paper is cited, I think, more than 15,000 times already. It's a very large number of citations because so many people are using it. And it's really widely used in so many areas, in image searching, object recognition, video checking, and robotics and recognition. It's used in so many areas. If you are interested in the methodology, detailed methodology inside the Sift method, then I do suggest you to download the paper and have a read on it. It's a really, really good paper, but it's a bit complicated to understand, but it's really a good paper. It's really, really a good paper. All right, so this is the history of the Sift. Then the question comes to, why Sift is so popular? Why Sift is so popular? So it probably must have some reasons, right? And if you can relate it to the question, what is a good feature, then we can find the answer. So the Sift feature is invariant to scale change. It is also invariant to rotation change, invariant to illumination change. It is robust to the noise. It is robust to affine transformation, and it's robust to change of the 3D viewing point. And it has high distinctive for discrimination. So if you can look at the properties of Sift, you can say it's invariant to most of the things, and the most of things are what we mentioned for a good feature, right? So that's why it makes the Sift that popular, because it's an ideal feature. It's a good feature. It's an ideal feature that we can use, right? And also here it doesn't mention that the Sift feature also provide a matching method, but a way to describe the feature and also use the way to describe the feature to do the matching, and that is another good thing, another very, very good thing. Then let's introduce the Sift. Then Sift has mainly two parts. Sift has mainly two parts. One is detector. One is detector. The detector is to detect where are the locations of the features. So the detector means it just gets the feature locations. All right, so that's the detector. And the second part of the Sift is descriptor, which means descriptor of each of the features. So which means you calculate a descriptor of that feature, and that feature can be described by this descriptor. Then you have features on image 1 with corresponding descriptors. Then you have features on image 2 has the corresponding descriptors. Then you compare the descriptors, and they can tell you if point 1 on the image 1 the same one as the point 2 on image 2, right? It can provide you the matches between images to tell you if this feature is the same as that feature or not. That's the meaning of this descriptor. That's why we have a detector and descriptor of the Sift. Then that's introduce the each of the part of the Sift feature. So the first part is the descriptor, which means the location of features, right? Then the first thing the Sift is doing is to do a Gaussian pyramid. The Gaussian pyramid. The Gaussian pyramid means it has different levels of image, and for each level of the image, it reduces the size by applying the Gaussian filter. The Gaussian filter. If you remember, when we introduce and calculate the convolution, and there's a Gaussian filter as well. The Gaussian filter makes it blurred. If you remember, make the blurred. And this Gaussian filter is similar to that, but it's not applying to a convolution case, but it can reduce the size. All right. So for example, if we have this image, then if we apply the Gaussian filter to get the half of the image, and then it will reduce the size of the original image by half on both XY direction, UV direction. And then if we apply another one on the second image, then it will be half comparing to the second image. Then after applying this, we can get a Gaussian pyramid. Gaussian pyramid. And that is the Gaussian pyramid, and we can do some calculation on that, right? Then why we are doing this Gaussian pyramid of the image is because it wants the feature to be scale invariant. All right, so different levels of Gaussian pyramid means different level of scales. Then it wants it to be a scale invariant. All right, and then after you get the Gaussian pyramid, and for each of the point, if you look at here, for each of the points on a specific level of the image, of the Gaussian pyramid image, is comparing the surrounding 8 neighbors, and also it comparing the 9 neighbors on both the upper level of the image and the lower level of the image. Then is by comparing them, is detecting the maximum and the minimum of difference of Gaussian in scale space. It's not on one single scale, it's in scale space. Right? Then the feature is detected as the maximum or minimum of difference of Gaussian in each of the level. It's a bit complicated. I'm not introducing it in a very detailed way. So if you just remember, there's a Gaussian pyramid. It wants to reduce the effects on the scale. Then the feature is detected as the maximum and minimum of Gaussian by comparing the features in different levels. Right? And then in this way, you're getting the features. That's the feature detector of Sift. All right. Then the next one is the descriptor. After you get the feature, then you need to calculate the descriptor of each of the feature, right? So the descriptor use the normalized region about the key point, and it computes the gradient and its orientation as well. So those sentences are quite hard to understand, but I'm going to showing you how to calculate the descriptors. All right. Then if you go to this figure, if you see the figure on the left, so this is an 8 by 8 area on the image with the center of the feature extracted in the feature detector, right? So suppose here is the feature detected, and then with that as a center, you get an 8 by 8 area. This is an example. This is just example, but in the real case is 16 by 16 area, but here is just example. So with that 8 by 8 area, then you divide it into 2 by 2 blocks. With each block has a 4 by 4 pixels, right? So for an 8 by 8 area, you divide it into 2 by 2 blocks, and in each of the block, there are 4 by 4, which is 16 pixels, right? And in each of the pixel, you are calculating the gradient, both the value of the gradient and also the direction of the gradient, right? Until now, it's easy, right? So just select the area and calculate the gradient. And the next step, if you look at here, how to get this? The next step is the gradient histogram. Is to calculate the gradient histogram. So we want to calculate the gradient histogram of each of the block, not each of the pixel. So here in this area, we have a 2 by 2 blocks, right? We have 4 blocks. And for each of the block, we want to calculate the histogram of the gradient. And what that histogram refers to. So in each of the block, we choose 8 directions. We choose 8 directions. And then we make the histogram with each of the direction and sum the gradient on that direction together. That's the histogram. Your histogram is about the directions of the gradient. And then if, for example, in this block, we have 3 or 4 gradients roughly on this direction, then we sum the value of the gradient together to get that number, right? So by calculating in this way, we have a histogram about the directions of the gradient in each of the block, all right, in each of the block. And because we have 8 directions of the histogram, and for each direction, there is a value about the gradient, sum of the gradient, then which means for each of the block, you have 8 number of values, right? Is that clear? Is that clear? Okay, so after doing this, what Sift did? Sift did exactly the same thing, but with different areas. So what Sift did is it used a 16 by 16 pixel area on each of the feature, and then it divided this 16 by 16 area into 4 by 4 blocks, and which means in each of the block is exactly the same as what we said here. So for each of the block is a 4 by 4 pixels, but the differences is in Sift features, so Sift descriptors, then it calculates on a 16 by 16 pixel area and divided into a 4 by 4 blocks. And in each of the block, it calculates the histogram of the gradient the same way as what we introduced here. Then if you remember, for each of the block, we have 8 numbers. Because we have 8 directions, then we have 8 numbers which represents the sum gradient on each of the direction, right? Then for each of the block, we have 8 numbers. Then for a Sift descriptor, there are 4 by 4 blocks. Then which means we have 4 by 4 by 8 values of each descriptor, Sift descriptor. Then which means the Sift descriptor is a vector of 128 values. 128 values. Is that clear? Yeah, let's go back to here again. So as we know, for a Sift feature, it uses the feature as the center, and it will get a 16 by 16 area on the image, 16 by 16 pixels area on the image with the center of the feature. Then it divides the feature, divides the 16 by 16 area to a 4 by 4 blocks. And in each of the block, it will be 4 by 4 pixels, right? So similar to what we have here. What we have here. For each of the block, it has 4 by 4 pixels. And for each of the pixel, it will calculate the gradient, both the direction and also the value. And then after doing that, for each of the block, it will calculate a histogram of the gradient value with respect to the directions. All right, and it used 8 directions, 8 directions here. And for each of the direction, it calculates the sum of the gradient value on that direction, roughly on that direction. Then after doing this histogram for each of the block, it has 8 values, right? And then because it's 4x4 blocks, then you have 4x4x8 values. That is 128 dimension of the descriptor. Right, so that is the descriptor of the Sift feature. It seems quite easy to calculate it, right? It's quite easy to understand, quite easy to calculate it, but it works really, really well. Works really, really well in the feature matching because we have descriptors. Then we can describe the feature. Then we can use descriptor to do the matching between different images. This is what we want, right? And that is what Sift proposed. All right, so the Sift has a lot of applications. For example, the image alignment, which can if you want to calculate the homography, the fundamental metrics, the insertion metrics, the relative pose, then you use this kind of features. When I first got into the video slam, then the first book I read is Multiple View Geometry and Computer Vision. I mentioned that before. Then I think the first hands-on work I did is to apply Sift features and calculate the relative pose from fundamental metrics of the two images. Right, and 3D reconstruction, they use a lot to reconstruct the environment. So if you remember, we have some examples about linear Roma in a day and also some kind of like SLAM, video SLAM applications. Then a lot of them, they are using this Sift features. Yeah, so especially for the 3D reconstruction, if you remember when we introduced the building Roma in a day, then it mentioned a feature must be observed in different images, and it needs to be linked together. And this work can be done by using Sift. You can apply Sift feature extraction on each of the image and use the descriptors to do the matching. Then you have the corresponding features in different images, and then it can be used in 3D reconstruction. And also, if you remember, when we introduce the stereo region, and there's triangulation, right? The triangulation is what we want to calculate the 3D feature location. But before we having that, we need to know the projections, the corresponding projections on the two images from the same feature. And this can be done by using the Sift as well. All right, and a lot of guys, they're using it by applying for motion checking and object recognition and robot control and navigation as well. So a lot of applications of the Sift. Then let me give an example about the Sift feature. So if you can see the two images have a very huge change on the weaving point, and also the scale and the rotation as well, right? And then after we do the Sift features, you can see there are a lot of matches. There are a lot of features and there are a lot of matches on it. Even they change the weaving point and the scale and rotation a lot. As you can see, the link lines, the link blue line, if they are parallel to each other, which means they are right, they are correct. They're most likely the correct matches. And for those kind of things, they are the outlier. They are wrong matches. But we still can have a lot of features. Still can do a lot of matches. Then let me run. Let me run the Sift code for you to have a better feeling about that. So this is the MATLAB version of the Sift then you can search on the website. You can download it, and also you can download the C version if you want. The original one is the C version. They make the max compiled file to make it run in the MATLAB version. And then let me run it, and you can have a better feeling. So now it's calculating different things, calculating the difference of Gaussian and calculating the image pyramid, the Gaussian pyramid. Then just detecting the features. There we go. So There we go. All right. So if you look at this, those are the difference of Gaussian's Gaussian Pyramid. Then if you look at the figure here, if you look at the figure here, it provides the features. It provides the features, and also by using the descriptors, it can provide the matchings between two images as well. Right. So those are the results. And let me run another example. Another example of the Sift. Yes, you can see Sift is quite slow, right? And that's why we introduced Sift. Okay, so here is the result of another example of the Sift feature extraction and matching. As we can see, the rotation and the translation and also the 3D weaving angle change a lot with the change of scale as well. It's a very huge change on the rotation. But in this case, we can still find that the features can be extracted, and for most of the features, it can get the matches correctly here, right? But still have some wrong matches, and we will introduce how we can delete those kind of wrong matches a bit later. All right, so this is the example. This is the example. This is the example of the Sift. So if you are interested in Sift, I do suggest you to download the code and apply on it by yourself. It's quite easy to run, and it works quite well for most of the cases. All right. Then when we run, if you remember when I run it, when we run Sift, you can find it's pretty slow, right? It is slow. Slow is the thing, because it calculates different levels of Gaussian Pyramid, and also it calculates the very huge dimension of descriptors, 128 dimension of descriptors for each of the feature. And then when you compare them, it will compare each of the feature about the distance between the descriptors. Then it requires a lot of computational cost, which makes it a bit slow. So in this case, people proposed Sift. The full name of Sift is Speeded Up Robust Features. Speeded Up Robust Features. So comparing to Sift, it speeds up in both the feature location and descriptors. So that is Sift. Sift is trying to speed up Sift, but with some approximations, which will sacrifice the accuracy of the feature. All right. So before we introduce Sift, I have some experience of both. I do suggest if the computational time or computational cost is not a big issue in your case, do use Sift, because the accuracy of the Sift is much better than Sift. That's my experience. But if you want to really reduce the computational cost, then you can use Sift. But the trade-off is the accuracy is not as good as Sift. All right, so it that is speeded up in both feature locations, in both feature detector and descriptor, and why and how it can be done. So the served for the feature detection, for the feature detector, if you remember for Sift, they use the Laplacian of Gaussian. Sorry, they use the difference of Gaussian to approximate the Laplacian of Gaussian. So which means it used the difference of Gaussian in scale space. But in Serve, this approximation make a little bit further, which means it approximates the Laplace of Gaussian by using a box filter. So just need to remember, it both needs to calculate the Laplacian of Gaussian. But for Sift, it used the difference of Gaussian. But the difference of Gaussian, it needs to calculate step by step. But in Serve, it approximates it with a box filter. A box filter can be calculated really fast on the image. The box filter can be calculated, can be applied on the image really, really fast. That's why Serve makes it fast on the feature detector. It used the box filter to approximate the Laplace of Gaussian. But this approximation is a bit far from the difference of Gaussian. So that's why it can make it fast, but it will not that accurate. Right? So that's the first thing for Serve. It's speeded up for the feature detector by approximating the Laplace of Gaussian by using the box filter. All right. Then the second thing is about speeded up in the feature descriptor. If you remember what we proposed, what we introduced for the Sift descriptor is, it use a 16 by 16 pixel area by divided into a 4 by 4 blocks. Then it calculates the histogram of the gradient on the 8 directions with respect to the 8 directions, and which we can get an 4 by 4 by 8 vector. Then that is the Sift descriptor. It's 128 values for each of the Sift feature descriptor, right? But in Serve, it calculated in a little bit different way. So I gave example here. So here, this one on the figure on the bottom left is what we calculated for the Sift, right? But for the Serve, we calculated in a very different way. We calculated as sum of the gradient on the x, sum of the gradient on the y, sum of the absolute value of the gradient on the x, sum of the absolute value of the gradient y. So which means in each of the block, it only has 4 values instead of 8 values, right? Then which means the total number of the Serve descriptor will be 4 by 4 by 4, which is 46, right? So for Served feature descriptor, it still use a 16 by 16 pixel area and divided into a 4 by 4 blocks. But in each of the block, it's not calculating a histogram of 8 directions. It calculate 4 values of only 2 directions of gradient. Then it makes 4 by 4 by 4, 64 values for each of the served descriptor. And that's the difference. All right, so it's still using 6 by 16 pixels area divided into 4 by 4 blocks, but for each of the block, it used 4 values instead of 8, and it's only calculating the gradient on 2 directions, x and y. All right, then why those 4 values can present most of the cases of these 8 directions of gradient? And let me give some example. For example, in this case, if the gradient on the image are purely 0, so it's like it's like a pure gray or black or white image, then which means on the x direction, the gradient is 0. On the y direction, the gradient is 0 as well. So the four values of the sum of the gradient, they are all 0, all very small, all 0, right? So that's the first case. And for the second case, if we have a figure like that, there are some blocks, black and white blocks. Then in this case, if we calculate the gradient on here, the x gradient on this direction is positive value, right? But when we calculate a point of the gradient on the white block, and it will have the same value of the gradient, but with the different direction. For example, if here we calculate the gradient as 10, positive 10, and here we can have the gradient on the x as a negative 10, right? And on the y direction, the gradient is 0, right? Here the gradient is 0, here the gradient is 0 as well. Then which means in this case, the sum of the gradient on the x value, on the x direction, it will be near 0 because you have positive 10, you have negative 10, right? But if we calculate the sum of the absolute value of the x direction, then it will be quite large, right? Because it's 10 plus 10 plus 10 plus 10, then it will be quite large. But for the y directions, they are 0 because the gradient on the y direction is 0. But if you have the figure, if you have an image on the bottom right, then which means you have a figure with the gradient continuously on one direction. And in this case, the sum of the gradient will be quite large. The sum of the absolute value of the gradient will be quite large, but on the y direction, the gradient are still 0. Then which means you will have 4 values like this. So that's why by only using the 4 values, it can present most of the cases, or some of the cases, but maybe most of the cases, we present it in the 8 directions. It's not in the 8 directions, but it still can present most of the information there. So this is what the surf did for the descriptors. It's 16 values of one descriptor, and it only calculates the 2 directions of the gradient in each of the block. As what we introduced, those 4 values, they can cover most of the cases, but not all the cases. And which means here the surf descriptor is still an approximation comparing to the Sift one, right? So that will make the matching a little bit not that accurate comparing to the Sift as well. So both of the for both of the speeding up in the feature descriptor and also the feature detector, surf make it faster by approximating something. Then which means the trade-off is the accuracy. It will reduce the accuracy of this feature extraction and also the matching. All right. Okay, so that is Sift and surf. Then, if you remember, when we demoed the application of Sift, we have this example. We have those 2 features, and we can find there are a lot of outliers, which means wrong match. There are a lot of wrong match. So in this kind of like figure, if the linking line is in green, if they are parallel to each other, they are most likely the correct matches. But if you find some linkings like that, so which means they are wrong matches. It's quite obvious in this figure there are a lot of wrong matches. And how can we delete those outliers or the wrong matches? Then we introduce ransack. RunSec is really commonly used in the outlier removal. It's not only for the feature matching case in the vision in the camera, but it can also use for many other applications, and it works really well. So RunSec is the second algorithm I implemented by myself. It's a very good idea, and it works quite well. It works really well. All right. So then let me introduce how the RunSec works. And I don't want to introduce it in this way. So those sentences will not help you to understand it clearly. Then let me give you an example about how the RunSec works. The example is not about the outlier removal in the feature matching, what we mentioned, but it's a very simple case. It's a very simple case about line fitting. So suppose we have those kind of features, those kind of points. We have a set of points, and then what we want is we want to estimate the best depth line fitted and remove the outliers. And it is quite obvious for us that the line is most likely to be here, right? Most likely to be here. And the outliers may be this one, and maybe this one as well, right? So it's quite obvious for us, but how can you remove it by your algorithm? Of it, how it can be done by computer? And that is RunSec, right? So for the idea for RunSec, for the first one, you randomly select the 2 points. You randomly select 2 points because 2 points is the minimum requirement to calculate a line, right? So suppose you have that kind of like point sets, you randomly select 2 points, then from those 2 points you can calculate a line, right? You can calculate a line. And then from that line, you can have a threshold. This threshold, in this case, will be the distance from a point to a line. From a point to a line, right? So this threshold will never change. You will never change. And after you have this line from those 2 points, you apply the threshold to say, so my threshold is the distance from a point to a line, which is smaller than 0.5 millimeter or 0.5 centimeter, something like that, right? And then you calculate how many points are within your threshold. And in this case, there will be 1, 2, 3, 4, 5. You have 5 points within your threshold, right? So that is for this one. And you remember those numbers. You remember 5. You remember 5 in this run. Then you have another one. You have another one. And in this run, you also randomly select 2 points. But those 2 points are different from the first one, right? And then you also apply the same threshold. And then in this case, you calculate, you just count the number, how many points are within your threshold. You're doing exactly the same thing as what you did in the first run. But in this run, you have 1, 2, maybe there's 3, 4, 5, 6, 7, 8, 9, 10. You have 10 points within your threshold. And this is the second one, right? And what you need to do is you run multiple times. For example, you run thousands of runs. You make thousands of runs or 10,000 of runs. And for each of the run, you just need to remember how many points and what are those points are within your threshold, right? And after thousands or 10,000 of runs, then you choose the run with the maximum number of the points within your threshold. And those points are your inliers. Is that clear? Is that clear? The line fitting. Okay, so let's go back to it again. Let's go back to it again. So for a line fitting case, so you have a set of points, and then what you want to do is you want to fit the best line and also remove the outliers. Right, so this is what you want to do in the in this example. Then what you can do is you do the first run by randomly selecting 2 points. By randomly selecting 2 points, then by using those 2 points, you fit a line. And then you have a threshold. You have a threshold. In this case, the threshold is the distance from the point to a line, right? And by applying that threshold, then you can get how many points are within your threshold. In this case, there are 5. There are 5, right? So that's your first run. And then you do a second run. You're doing exactly the same thing. You randomly select 2 points, fit a line, apply the threshold. Then you can count how many points are within your threshold in this run. In this case, there are 10, right? And then you keep doing exactly the same thing, but starting with randomly selected 2 points. And you repeat doing this. Then after you run 1,000 or 10,000 of runs, then you have the numbers of points in each of the run. Sorry, within your threshold in each of the run, and you choose the run with the maximum number of the points within your threshold, and those points are your inliers. So for in this case, we may choose the run in this case, right? And after we choose that, because in this run we have 10 points in my threshold, but the other runs they don't have 10. So this is the maximum. So this is the run with maximum points within the threshold. Then in this case, the points in the thresholds are your inliers, which means that the wrong point, the right point. And the points outside of your thresholds, they are outliers. They are outliers. All right. So this is the case. This is the case for the runsec for the line fitting example. How can we apply it to the feature matching case? For the feature matching case. So in the feature matching case, what we have is we have a set of correspondences. We have a set of point matches. Suppose we have a 400 or 500 point matches between the 2 images. And then most of them, they are inliers, they are right matches. And part of them, they are wrong matches, we call it outliers. And our aim is remove the outliers from the correct matches. We call them inliers, right? So we want to remove the wrong matches, the outliers from the inliers. And what we can do nearly the same thing as what we applied to the line case. All right. So the first thing is we introduce the epipolar constraint here. We introduce the epipolar constraint here. The epipolar constraint is if you have 2 images, you can calculate a fundamental matrix F here. A fundamental matrix F here. And that fundamental matrix is a 3x3 matrix. You don't need to know how to calculate it. There are a lot of papers about how to calculate it. But do remember, if you have 2 images, there is a fundamental matrix here. There's a fundamental matrix here. And if you have a pair of correspondences, so suppose you have a pair of matches, which means a projection on the left image and a projection on the right image corresponding to the same 3D feature. And then you put them here, You put them here. You put the one on the left, the one on the right, on the both sides of the fundamental matrix. If they are right matches, it will be equal to 0. That is the constraint. That is the constraint. And this is the constraint you want to use. You want to use as the constraint in the line case. That is the constraint. All right. And this fundamental matrix will be the line you fitted from the 2 points. All right. So if we go back to what we have in the line case, in the line example. So the first thing is we want to choose randomly choose some points to calculate the line, right? So in this case, we want to randomly choose some matches. You can choose 5, 6, 7, and 9, or 8. So there are a lot of algorithms from a pair of matches. Then you can calculate the fundamental matrix F. There are 5-point algorithms, 6-point algorithm, 7-point algorithm, 8-point algorithm, or whatever. You choose, suppose you're choosing 8 points, eight pair of matches from your set of 500 matches. And you can, from the 8 pair of matches, you can calculate fundamental matrix F. You can calculate the fundamental matrix F. All right, and then after you have this fundamental matrix F, you use this F to test all the other pairs, all the other pair of matches by using this equation. Right, so after you have the fundamental matrix F calculated from the randomly selected 8 points, then you can use it to calculate each pair of other matches, 498 matches, by using this equation, by calculating this equation. And you can give a threshold. It's ideally it's supposed to be 0, but it will not be 0 because there are some errors. So you can suppose this matrix, so this equation, my constraint, will be 0.5. All right, then you use fundamental matrix to test all the other points and to calculate how many pairs of matches are within 0.5, which is my threshold. You count those numbers. That's your first run. And then your second run is you randomly select another 8 points to calculate this fundamental matrix F, and then use that F to test all the other pair of matches. And then for each of the pair you have a number, and then count how many pair of matches they are within your threshold, which is 0.5, for example. Then you have another number, right? And after you run it thousands or 10,000s of times, then you can have for each of the run how many pair of matches are within your threshold, and you can choose the run with the maximum number, and the pair matches within that threshold in that run will be your inlier. All right, so that is the run sec to remove the outliers of the matches of the feature matching. All right. So if you don't understand, try to think about the line case first. That's the same idea as what we have, but in our wrong feature matching removal, then we need to randomly select 8 pair of matches for each of the run to calculate the fundamental matrix F here, and then to use the F to test all the other pair of matches and to see how many pair of matrix they are within the threshold. They are within the threshold, and you do multiple runs and choose the run with the maximum number. And in that run, the matches within the threshold, they are inliers. All right, so that's the ransack outlier removal. And this is an example about the ransack outlier removal I implemented myself. This is a data set by a drone, by a UAV, and in our old CAS lab area. And let me run it. Let me run it as an example. Okay, they first do a Sift feature extraction and matching, and then do a ransack. The figure on the right, it is the feature extraction and matching without ransack. You can see some kind of like features, they are wrong features because the line are not parallel, right? But after ransack, they reduce the number of the matches, but they removed the outlier as well. So as you can see, if you can see this match, it is a wrong match, right? There is the point on the near the light, and here is a point near the table, right? So that's a wrong match, and after the ransack, it reduces it, right? It remove it already. All right, so that is mainly for today, and then for in the next lectures we will start the control part. So in the control part we will have 3 lectures. The first one is the linear case. The linear case for the linear continuous time control. And the second lecture will be still the linear case, but it's discrete time model. And the very last one for the control part will be the nonlinear discrete time control, which is quite close to the real case. And then after the three lectures about control, we will have an integration of the sensors and control. And in that integration, the ideal case is the visual servering. So in that, after 3 lectures about control, we will introduce the visual servering. All right, so that is all for today, and let's move to Malin for the handout activities. I think most of you have already do something on the feature extraction and checking in the last tutorial, and then Malin will do something else today about the tutorial, the handout activities. All right, so thanks for coming to today, and let's move to Malin. Thank you.